All right. I would like to start by thanking Gerhard and Jan for inviting me here, and also for scheduling Andre just before my talk. I could not have had a better introduction, actually. So this talk is I entitled it Precision Tests of Quantum Interference, and what we're going to look at is first Bournes Rule. So we already had Bournes Rule. And I'm in particular interested in interference, and I'll show you how higher order interference was, I guess, proposed as just a way of classifying general probabilistic theories. It doesn't mean that there are any explicit models that predict these. And then I also have a little section at the end about quaternions. But then after sitting next to Stephen Adler yesterday on the bus, I'm not so convinced anymore that this is actually useful, but you can take your own conclusions. All right. So let me start by introducing the people who did this work, experimented. Thomas Kauthen and Benjamin Schösser. And now I also have a new master student, Thomas Kaufmann, who's working on this part of the project. You can see there's many more people who do other stuff, which you will not hear about today. So I should also acknowledge the organizations who fund this, although it used to be the Foundational Questions Institute, and it's also CFAR. The lower ones actually don't have so much to do with this work. I should also acknowledge collaboration with Czeslaw Bruckner on this topic, and with these two people, Ubushi and Thomas, at the time in Waterloo. Ubushi is now in India, back in India, and we've handed in a proposal to continue these studies. And then also for the last part, I now have waveguides from Alexander Samite in Jena, with the hope of improving some of these tests. All right, let's start with Bournes Rule, which was detected or discovered in a footnote, telling us that it's really the square of the wave function that's supposed to be a probability. Of course, you all know that, and there's various versions in which we can write this as a psi square or as the trace rule that we just heard from Andre. They're all the same. And we also know that this is really at the heart of interference. And of course, this would be true for, I guess, almost any wave theory, linear wave theory that allows superposition principle and has a square functional for whatever you detect, intensity, power, or probability, as we have in quantum mechanics. And perhaps in classical wave theories, that doesn't really discomfort you, but in quantum mechanics, where we also count clicks, then many puzzles come out of this. And so if we define interference by sort of the difference between what one would expect in a classical probability theory, so if I shoot at these slits with a shotgun and just record how many I get, and then I assume that if I open one slit, I get a certain number of particles in a particular point at the detector or screen. I open the other one, I get another number, and then if I open both, I should see the sum, but of course I don't. If I do this, for example, with photons or with electrons, then I find that if I subtract these probabilities from the probability when both are open, and I can call this my interference term, IAB. And so nothing new here. If we go to 3 slits, there's also nothing new. And that was something that I will admit hadn't realized before I actually got into this work at all. And that is that, of course, all interference terms that appear here are bilinear products, and therefore they are sort of interference occurs in pairs of paths, no matter how many possibilities you have. Of course, assuming that these wave functions here are orthogonal or non-overlapping, or in Raphael Sorkin's speech, they're mutually exclusive events. And so if I now expand this by replacing these interference terms with their definitions that I took from the double slit, I get this long expression which can be simplified into this, saying that the 3-path probability is really just the sum of the 2-path probabilities minus the single-path probabilities. And now I can say, well, could there be anything more? You know, how well do we know that there's nothing more than that? And it turns out we didn't know, at least not until a few years ago. And this was how Raphael then said, well, we could, if we had general probabilistic theories, we could classify them by the amount or ways in which they disagree or deviate from classical probability theory. And he proposed that sort of the first unconventional interference term, the second order interference term, would then be defined as, so this is IABC, the three-path probability minus all the stuff that's on the right-hand side here. And obviously, it is clear from the calculation above here that in quantum mechanics, this would be identically zero under any circumstances. So it means that these slits here, A, B, and C, they can be of any type, any shape. They can be all different. It doesn't matter. As long as you do measure these sort of independently, you measure these terms here, it will be zero. And that's good in a way because it's a null experiment, right? We're trying to prove the absence of something, and it's always better to find a zero with an error bar than to find a finite quantity with an error bar. It's usually easier because there's no systematics. At least that's what we thought. Now, this is sort of symbolic representation of all the measurements we would have to do, and then there's one consideration that we have to add here for the experiment. There's also P0. When everything is closed, we still detect something. We just heard about this from Andre. So we discussed it with Raphael, and he said, well, there's no problem at all, because I can just give a certain probability to the empty set. And so if we treat this consistently, we pull it through all the calculations, we get to exactly this formula. So it's like the probability of nothing. Yeah. Okay, and then there's also some normalization. So because it's really hard to get a feeling for how large this epsilon should be, we normalize it by the amount of interference that we expect. And so the quantity we measure is the amount of unexpected over the expected. And if you do this experiment with something where there's no interference, then this could blow up, of course, but in fact it doesn't. At least usually the epsilon will go to zero faster than the delta in some classical experiments. All right, and then there's the big if. What happens if we now find something seriously non-zero here? Of course, we would like to go to Stockholm to pick up a prize, but we'd probably get a lot of flack before we did that. Obviously, Schrödinger's equation, the unitary evolution, preserves the norm of the Hilbert space vectors. So if we now claim that the probability is not the square, then somehow probability gets lost on the way. Could be helpful, but might be catastrophic too. How about classical physics? We do these experiments with photons. So what we measure really is the energy density of the Maxwell field. And if you think that this is not, so unless we believe in Andre's detectors, this would be very discomforting, right? That the energy density of the field is not a square of the field. But maybe Gerrit has something to say about that. And there's a few other interesting consequences. Scott Aronson proved that if you deviate only by epsilon from the square in Bournes Rule, you can actually have a quantum computer that post-selects itself, and therefore you would collapse the polynomial hierarchy. And for computer scientists, that's even worse than having a breakdown of quantum mechanics. And then there's something nice by David Meyer and along these lines too. And there's also a paper, and I have to say I haven't analyzed this completely, that establishes a connection between the absence of higher order interference and the Zierelson bound for non-local correlations. And I find that interesting. I still have to learn a bit more about that myself. Okay, so I'm an experimentalist, so I'll show you an experiment, and this is a very simple experiment. That's the old experiment we did in Canada. There's a laser, there are some slits, and there's some way of blocking and unblocking the slits, exactly as you would imagine. And then we get some diffraction pattern somewhere far down the line. We take a tiny fiber, and it picks up the photons at a particular spot, and we measure them with a single photon detector. We also do this with a single photon source. Let me just skip over that. So here are our slits. They were cut into a metal membrane, a steel membrane, laser cut into steel membrane, and there is also a sort of a similar steel membrane that has openings for these slits. So they were brought into sort of almost close contact, not actual contact, and so we can slide the one mask up and down and sort of open or close these slits. And you will see that these are much bigger than those, so about twice as wide and also higher, so that the diffraction of these supposedly wouldn't matter. Okay, and so then we did some measurements, and if you count it all together, we could bound this higher order of interference to about 1% of the expected interference. Not a very strong result. In fact, I was not very happy about that, because I thought that's kind of a weak proposition to just, we would have detected this before if there was a deviation of that order of magnitude. And what was the problem? The problem was that this opening was actually not very well aligned. So the thing that opened the B slit in the BC combination was a bit out of alignment here, and it turns out by near field diffraction effects, this actually changes how much light goes through the slit. And so there's, we want to do these measurements independently. We want to measure these 8 terms independently, but this actually introduces a correlation. The B is not the same B in all the B measurements or in all the combinations where B appears. Another point is, and this was pointed out by Hans and Crystal, is that obviously if the slits are close and I use finite conductivity materials or finite absorptance materials, there's some back action, right? And there's crosstalk. If I close a slit, this will actually modify the wave field, and therefore these functions, these wave functions that I use, psi A, B, and C, are not orthogonal. And if they're not orthogonal, then we actually expect some of this interference, some of this higher order interference, simply because we do not fulfill all the premises. And I think almost the same, but in a slightly different language. My collaborators in India did a calculation where they calculated this in a kind of path integral formalism and took into account loop paths through the slits. And obviously this will also give some kind of exponentially decaying value of the higher order interference. The farther the slits are apart, the less likely will it be that you have effects from these loops. So all of this tells us that slit experiments are difficult. On the upside, though, we got a nice letter from Gustav Bournes that said he was very happy to discover that somebody actually cared about his father's rule, and he encouraged us to do more experiments in this line. I think we replied that actually many more people care about it. They just don't talk about it every day. And I should also mention that other experiments have been done, because eventually you would not like to do this all in the same system. So this also uses photons and used some kind of imaging and spatial light modulator equipment to do the various combinations. And then the only experiment that uses a significantly different physical system, so this is done in nuclear magnetic resonance with measurements of certain occupation probabilities of spin states in this molecule here. You can see that the precision or accuracy they got is about 1 order of magnitude better than we got in our first experiment. And in fact, I believe that we will have to go away from optical experiments if we want to get much beyond what we have so far. But then, of course, we weren't sitting idle ourselves. So we instead of doing slits, we went to interferometers. And I think for a long time I've been saying that whatever you can explain with slits, you can explain better with interferometers. They're just not as familiar to some people as the slits. And we bought a very simple grating beam splitter, a device that by diffraction, it's essentially a hologram that takes one laser beam, like the one I have here, and splits it into 5 equal intensity beams. So then we collimate these beams, and then we have a shutter array, which I'll show in a second, where we recombine on the same kind of beam splitter, and we get one beam out that is a superposition of all the 5 input beams. Some interesting questions about what happens to the other diffraction orders here, because there's actually not 5, but we will have about 9 diffraction orders coming out of here in general from these 5 beams. And that is an interesting question. Can you even have a true multi-port beam splitter, and how many ports can you really have? I think that's an interesting question. But in any case, the nice thing here is that we can actually, you can stick your finger in, so you can block this beam very independently. You will not induce any correlation. I can really separate these paths. And now if you think about loops, possible loops or crosstalk I guess in terms of near field interference, it's virtually impossible, because a loop has many centimeters actually around here compared to the wavelength that is gigantic, and the separation is huge. It's a few millimeters large. So why 5? Well, it's very simple. We bought this element here, and it had 5 beams. Okay, so we only used 3 at first. But then actually, and my students said, why should we do 5? We have to measure, 4 times as long if you want to measure all the combinations, because now there's 32 instead of 8. But it turns out it has one nice side effect, and that is that this 5-path interferometer contains 5 4-path, 10 3-path, and 10 2-path sub-interferometers. And now you think, well, this is kind of redundant, and redundancy is good, right? Because if there's any systematic effect, then maybe one of the shutters doesn't operate well, or so. You will notice it. It will not fool you into a false positive. So that's an advantage. There's also an advantage in that we can see more exactly in terms of modeling. We can look at the behavior, say, if the detector does anything weird. We can see how it does it weird. In modeling it, we can much easier fit to 32 data points than to 8. That's good. And if we wanted to find out more about how Bournes Rule was broken, in case it was actually broken, we could get more information in that case. And then there's some explicit models that might actually predict a certain order of the violation, and this could also be detected better with a multipath interferometer. So here's the picture, and there's actually phase plates, macroscopic plates. We can change the phases of all these beams, and we have to control them too, which is not that easy, by the way, but it's stable enough that it works. And there is a nice shutter assembly, which is now black, so that it doesn't scatter so much light, but this is still a silver picture with little model airplane servo motors. So this is what I call a light valve. It's like a valve, and it opens and closes the paths. All right. I said the interferometer is very stable, and in fact, so this is dark counts or dark voltage, and this is the single paths. This just tells you how stable the laser is. But these are the 2-path interferometers. These are the 3-path interferometers, the 4-path interferometers, and the 5-path interferometer. And also that is quite stable, except that I've blown up the axis here so much that it looks a little wavy. So that is good. We can do measurements for long times, and we do need to do measurements for long times. I've gone here through some simulation of, so this is the counts or the signal in all these different paths. What we haven't done yet is a complete tomography of the state that we get, and we're doing this right now in order to understand, at least on the quantum mechanical level, what we're seeing. And then the results. I've tortured you long enough with all the details. So here are some results. This is with not with a photon counter, but with a linear photodiode. And we find these values of kappa. So this is the third order interference, second order interference term, third order, fourth order, are in the 10 to the minus 5 range. But if you look at this carefully, in this notation, this is the uncertainty. The uncertainty is in the last digit. So it's actually, the value is 10 times bigger than the uncertainty. So you'd say this is significantly non-zero. okay? Let's look at the next result. Oh, it's also significantly non-zero, but on the other side. So what's the reason for that? I'll show you a third measurement. So this is with photon counting. Now we're again on the minus side. And here we can't say. It turns out photon counting is nice, but it also takes a long time. And my students so far weren't willing to run this for a whole year because they want to graduate at some point. So we'll see how we can speed this up in the future. But what's the reason? What we believe the main reason for this non-zero value, significant non-zero value? There's one systematic effect that we haven't discussed and has very much to do with what Andre was talking about. It's the detector. A real detector is never linear. Okay, as Andre said, it's complicated. There's some ways of creating gain, and in fact, no matter what instrument you use, what transducer, there's an input and an output, and there's a range, and over that range, it may have a certain level of linearity, and the Standards Institute care about this. And how do we measure this? We can take what's called the beam combination method. So there's two lasers, totally independent lasers. We put both of these lasers on the detector, measure the power, and then we switch one off and we switch the other off. We also switch both off, and we measure the power. And now we can look, if the detector is perfectly linear, then the signal with both lasers on would be exactly the sum of the signals with each laser on. And we can do this, and what do we find? Here's our photodetector, and this is a photodetector that's been made to be particularly linear. And in fact, we discovered that nobody's measured the linearity of photodiodes as precise as we have, surprisingly. And most of these papers come from Standards Institutes people like NIST or the Swedish one. So this is a nonlinearity of 25 parts per million. And if you look at this, so this is 10 volts here, is the total signal. And the nonlinear deviation, this is the residual signal, or the missing signal, if you will, is about, well, here's 1 millivolt. So this would be, wait, no, that must be wrong. 1 millivolt, 10 volt, 1 millivolt, that's about 100. But, so this is about 100 here in this curve. And now it turns out if I plug this into a simulation, I find that my kappa should be about 1 times 10 to the minus 5. So I have some, the conclusion is I have some reason why it would be non-zero, but I can't explain the full level of non-zero-ness yet, okay? This is the conclusion for this detector. We can also look at avalanche photodiodes. These are much more nonlinear because they have a dead time. They detect the photon, and then they're blind for a little while. So I can't actually detect another photon, and that means that for high count rates, it just saturates. You know, at some point it will always be on. I will not get new pulses anymore. This could be improved if we had a proper single photon source in this experiment. We have one, but it's a continuous wave one, which doesn't eliminate the effect completely. So we're still working on that. And if we take this, then we can measure kappa as a function of our count rate, and we see that it actually, it looks very linear, and it's almost linear to quite some large numbers. And what we can now do is we can take this nonlinearity that we've modeled with the dead time and extrapolate to 0, and we find also, oh sorry, that number is actually not quite correct. We find that our kappa is, I have the exponent wrong. There should be a 10 to the minus 4 here if we extrapolate this photon counting result to 0. All right, so this is the status of the higher order interference. So far, our bound is in the 10 to the minus 5 range, and it depends on the specific detector we use. So it's not completely universal. I think with our technologies, we can go maybe 1 or 2 more orders of magnitude better, but that's the end with the photons, at least in my lifetime, of measurement time. And now, maybe for the last 2 minutes, I think, do I still have 2 minutes? Yeah. I will say something about quaternions, which is a bit of a sadder story, actually. So here are the quaternions. Quaternions were very popular a few times in the history of mathematics and physics, both in electrodynamics and also for they're actually used for nowadays for calculating rotations in computer graphics for certain reasons. And this is the rules for quaternion. It's a four-dimensional thing, I guess an algebra, with three imaginary units, an I, a j, and a k, and they fulfill a certain multiplication law, and they're non-commutative. And here is the inscription when about Hamilton when he discovered the multiplication law for quaternions. And so the question is, Andre said before, you know, we always puzzle about the complex numbers in quantum mechanics. Why not quaternions? And I talked to Stephen Adler yesterday about why one would even study quaternions in quantum mechanics, and there was some ideas about problems that they might solve. Now, Asha Perez proposed a test to figure out whether quaternions could be there in nature, whether quaternionic quantum mechanics would describe nature. And this works by pretty much the same thing we do here. You take a two-component wave function, and if I express this norm here as the PA plus the PB plus the interference term again, then I can look at the angle between these two vectors, and I can calculate this angle in the way I've shown here. And now if I do this with 3 again, so here again our three slits or our 3 interference paths, then these angles are not all independent. In fact, they have to sum to a whole circle. And Perez put this into an expression here that relates the cosines of these angles. And if our f here is 1, then that means that the psi's are represented by complex numbers, and these angles all lie in a plane. If you now think of this thing as lying on a cone, then the angles will not sum to 1, right? The angles of these rays on the cone. And so for f smaller than 1, these angles are not coplanar, and then quaternion psi's would be allowed. Okay, all right, we thought that's an easy experiment. And here's our f measurements, and oh, it's not even one of them that's 1. They're all smaller. Okay, we have not discovered quaternions, unfortunately. We wish. It turns out that so the Sorkin experiment is very nice because it's completely sort of intrinsically free of systematics, as long as you don't count the detector. However, the Perez experiment is plagued by systematics. It requires perfect coherence. If there's any finite visibility in the interferometer, then you cannot do the test. So this, we could, of course, now, and this is just a plot of what the expected f is, and it varies wildly and widely. And in fact, it's just in here. If we calculate this cosine, if there's averages in here, and if we average over incoherent amplitudes here, then, or probabilities, then this will not be the proper cosine anymore, and will not be 1 anymore. So even though I don't know if this is a useful test, we're trying to improve it, and so now we have a waveguide chip that actually implements a 3-way coupler on the chip, which between 3 single-mode waveguides. So in principle, these should be perfectly coherent. I don't see what else could reduce the coherence in there. However, this is not a full interferometer. We don't know yet how well. We're trying to reflect the beams back with outside mirrors, and then maybe we can tweak it far enough so that we can make a statement about this Perez criterion. If it's useful is another question. I heard that we really would only need to look at very near-field optical effects rather than anything like that, but this will be to decide in the future. So let me conclude by reminding you of the things I discussed. I said that we tested for higher order interference, and to a certain level of precision and accuracy, we've ruled out the existence of such an interference. And right now we're working on testing for hypercomplex numbers, but we need better criteria or higher visibility or both. Thank you very much. Great, 29 minutes.
So thank you very much. Questions here in front?
Repeat the comment I made, Gregor. In my book, I'm going to bring out a quantum mechanics. One of the main reasons
Microphone, maybe.
scattering theory is always complex. So that means that the parts of the waves that have an e to the IPR dependence are in fact all reducible to one complex number. And therefore you don't see the kinds of effects that Paris was proposing. That's because of quaternionic effects you can show all decay is e to the minus PR. They decay exponentially, which means you have to go to the near zone of scattering to try to do a test. That's, of course, experimentally harder than going to the far zone. I've been advocating to the people who are thinking about this, maybe they should think about microwaves, or maybe the kinds of things that Thomas Edison initiated, showing that when you have lots of little holes drilled in a plate, you get surface plasma on near zone effects. But if you just try and look at the S matrix, theory says you should see nothing.
Do you want
Right.
to
No,
react on this?
I'm happy about the comment. I couldn't have said it that well.
Okay, another question?
It's not actually a question, it's just a comment about your nonlinearity problems. I don't know what lasers you're using, but they are notoriously for drifting over time. And
Which?
So I'm saying, I don't know what laser you're using, but lasers in general are notorious for drifting over time.
Right.
And also, I've found to my own cost that even the data acquisitions, the electronic systems, drift over time as well. And you really should have them on for a long time, and I'm talking about independently, and check these things, because they can add up, you know, and your non-linearity can start off a little problem, but actually over time can actually become a big problem, as it were, you know.
I will say the following. In measuring the nonlinearity, the stability of the laser is a problem for us. In the experiment, however, when we measure these different combinations, the different power levels we apply to the detector are much more different than what would be caused by the instability of the laser itself, right? Because it goes from dark to, there's the single, the 2, the 3, the 4 path, and they all have different power levels. So we explore, it's essentially the dynamic range that between the dark level and the brightest level that will control or that will determine how much nonlinearity we pick up in the detector. The instability itself is more a problem with the precision. So the distribution that we find, you know, that of course is governed by the stability of the laser, but not necessarily the offset.